Okay. So this is going to be a review today for the topics, and in particular, I would like to hear from you which topic you want me to kind of explain things, which might have, um, which you may have some more questions about, which you may need more clarifications about. That's the purpose. I would like to hear from you. And then after that, I'll present this paper, and we'll try to get done early today because I know that you have probably several things going on at this time of the year. And just as a reminder, we will have our exam, which will be administered through the honor lock as per the Oscar schedule. I believe it is on Friday. Is it? Can you clarify, Nathan? Is it from 5 to something or?
Yes, it's on Friday. Man, I've looked this up so many times. I think isn't it 6 to 8:50?
Oh, is
Yeah,
it?
I think that's something like that.
Yeah.
Okay, 6 to 8:50. Okay, what a time. Unfortunately, we had to stick to whatever Oscar tells us. We have no leeway. I tried doing it once and I got in big trouble. So, because it can collide with somebody else's exam and it can come in the way of your preparations and all these things. So, we are really not at liberty of making any change. So, we'll go with Oscar, and you log into Canvas and you'll see the honor lock exam there. I hope all of you are onboarded or uh, try to take the practice test, and we'll talk about the exam just in a minute after we finish a little bit of review. And so that's basically, if you haven't done the practice test and gotten onboarded, then please do so at your earliest. All right, so let's do a review of these different topics that we have seen. And the good thing about the silver lining to this pandemic, and we had to do this remotely, is that we have the recordings of all the lectures, which doesn't happen in person classes. And you have all the, of course, slides and different reading materials also, which are posted on a module by module basis. So I'm going to go through those and then pause and then ask you which questions you may have, and then try to clarify those, maybe use even slides there, and then we'll talk a little bit about exam and then get into the paper which and the presentation about it. That is not on exam, as I was mentioning, the network processor paper and the presentation that accompanies it. But the register allocation topic that we finished last week is on exam, and I have put those slides there, and you of course have the recording of the lecture as well. All right, so let's go through these topics. So we covered a bit of material in this class. Mainly this is the back-end side of the house, which deals with presentations. And we started with the, of course, the overall working of the compilers, and we did some reading about some of those topics about how the parsers work and those kinds of things through the assigned reading which I had given. I hope many of you probably have gone through that and acquainted yourself with the front end side. But this class really starts with the intermediate representations. And what are the different kinds of intermediate representations we saw? We saw mainly the one which really starts with the parse tree. That's the one when the source program is parsed by the parser and arranged in a hierarchical sense as a part of the tree, using operator precedences and breaking down the sentences in terms of the parts of speech as per the grammar. And that's where the first IR is. From there we have AST IR, which is sanitized by removing all these parse symbols, the grammatical non-terminals, etc., which we don't need to have. and that tells us how the expressions will look like when they're broken down in terms of the operator precedences and things like that. How are the different statements, if then else loops, they will look like in terms of their bodies. And then the first translator we saw there was IR code generator, which walks these trees at the AST level and converts them into our first big IR, which is quad or triad kind of an IR with the fields, operator, operand 1, operand 2, and then the destination or the result. So this is the most important IR which is used in all the backend optimizations, and we looked at different algorithms which will convert this AST into this particular one, including how do we deal with short circuit operators, etc., etc. From there, we went into control and data flow analysis, which is the next module, which is really one of the most important ones as far as the data flow and control flow analysis is done. And we saw what is the control flow graph representation here in terms of basic blocks and their representation, which is in terms of a sequential set of statements in the IR, which execute in the lexical order. And we wanted to go for the maximal representation because then we can really reason about the properties within a basic block. When we enter a basic block, of course, there's no guarantee we'll execute a basic block, but if we enter it, we'll always execute it in that particular order. And this ordering on the statements allows us to understand the properties of data flow, how it will go from one statement to the other, and will allow us to try to keep a value in a register, and the IR is really important here. Otherwise, if we don't know where the control flow will go from one statement, whether it will go to the next statement or whether there will be another some other control flow may occur, and suddenly the control can come into the next statement from somewhere else. If that is possible, then we have to account for the data flow that accompanies it. So what basic block does for us is tells us that, hey, from statement 1 to statement 2, that's the only way the control flow will occur. There is no other way the control flow will suddenly come in to statement 2 without going via statement 1. And because of that, we know that these statements will execute in a particular order, and therefore the data flow that will accompany will be as per these sequence of executions. If the control flow could suddenly come in and come to the statement 2 without going via statement 1, then maybe it will bring another value associated with it to statement 2, and we must account for that particular value. I showed through examples that optimizations such as the constant propagation, even register allocation, they do not become safe if we don't have this guarantee, because in one case, as you can imagine, if a value can come via the control flow to statement 2, then we have to account for that value, and the two values, one coming from statement 1 to statement 2 and another one coming via another route of control flow, may not allow a constant to be assigned to a particular flow that comes out of 1 to 2. So that's the reason why we need this particular analysis for basic block, and we want to make it maximal to be able to reason in the maximal way about it. And the same is true about even register allocation, because if you're allocating a register to carry a value from statement 1 to statement 2, if the statement 2 can also be reached via some other control flow, then the use of that value must have a web, which comes from a definition coming from 1 to 2 and some other definition which can reach via that control flow, and we must mine both of these to the same register. So any such thing, data flow, which we need to reason about within the IR statements, needs this understanding. And so we started by doing basic blocks there and identify basic blocks. That gives a certain understanding, but that doesn't give us a big understanding. So we extended this to the whole control flow graph within a given procedure. And that control flow graph allowed us to reason about which values go from where to where, things like that. And that's one level of understanding. And from there, we decided to focus on the loops and detected the loops at IR level using the concept of dominators. The reason here is we have the single entry loops, which can be only entered at the top using a unique node, which is a dominator of that cyclical subregion. And all the natural loops, like all our if-then-else statements, not if-then-else, all the looping constructs, while statements, and so on, they all allow us to do this generation of the natural loops. Programming languages typically disallow you to jump in the middle of the loop, and that's why the single entry is sort of a sound way of writing a loop, and that's what the languages kind of enforce. So 99.99% of the loops are natural loops or single entry loops, and they can be detected by using this mechanism of dominators and back edges. And we saw those, and that allows us to do a very quick determination of a loop in a very structured manner. And we saw many examples of these. And then we moved on to things here which were about data flow, which is really, really important. So while control flow allows you to go from one place to the other, whether or not the value is carried by an actual definition from point A to point B is determined by whether the definition reaches using some path, which is a valid path, to this point B. And for the purposes of static analysis, we do over approximation, and we assume that all these paths are feasible. And unless we prove that it is not feasible, which is what you saw maybe in your projects, and we were able to remove some things and some definitions which are going along those paths. But under the assumption, we cannot disprove it. We must assume it reaches, the value is carried by that definition, and in between, if these things get redefined, that particular definition is not able to reach if it's not allowed along any path. So along every such path, if it is redefined, if some other definition comes in its way, then the original definition doesn't reach the destination. If it somehow manages to find one path, then it will reach. And so this we formulated as a data flow problem of reaching definitions and found those properties and found out what are the reaching definitions and so on. And then we talked about UD-DU chains and some ways of using them to do certain optimizations like constant propagation. So that was the core data flow problem. And then we saw some other problems like copy propagation, the common sub-expression elimination, and so on, which allows us to reason about the whether a particular copy is prevalent, and copying and CAC, they're the same problem. which tells us that if a particular sub-expression is available somewhere because it is available along all paths and is evaluated before this particular point. So that allows us to reason about redundancy, that if something we are doing again. And it's a lexical notion of redundancy, which is saying that, hey, A plus B is the sub-expression, and again we are doing A plus B downhill somewhere in the control flow. And therefore, the second execution of A plus B is redundant. So we are able to do this redundancy determination using lexical notion. Lexical means A plus B and A plus B. So are deemed as redundant, not A plus B and P plus Q, which could be redundant because they are equivalent in terms of values, but it's not caught by this analysis. So we did this, all these things in this particular process. We also looked at the very busy expressions, what they mean, what their implication is. And then finally, as a last topic in this particular direction of data flow analysis, we looked at partial redundancy elimination. So what is exactly partial redundancy? Partial redundancy is the expression is partially available, so it is evaluated and it's in our hand along some paths, but not all, and therefore we cannot eliminate it at a certain point. So it could be partially redundant, but if we come along some other path, it may not be redundant. It is not redundant, in fact. So then how to deal with this? We looked at the formulation here by Dreckler and Stradell, and we looked at lots of nice examples why we need to go to the concept of earliestness, and here was a big trade-off that is involved between what we call as availability and anticipatability. So we saw what is anticipatability means. It means that at this particular point in the program point, if we go down from this program point in every possible path, on every such path, we will have an evaluation of this particular expression before any of the operands are redefined. And so because of this anticipatability, we know that we are not introducing anything superfluous on any path or anything which doesn't evaluate on those paths. So we use this anticipatability, and what we try to do is we try to hoist an expression in the path of non-availability till we do not violate anticipatability. We don't introduce additional computation on any path, and we go as high up as possible using this condition, and we try to cover the expression along the paths of non-availability. Now that is the way we get rid of the redundancy. But then from there, we don't want to leave these expressions there at the earliest points, although we could, and be done in terms of solving the problem correctly as far as the non-introduction of non-anticipatable expressions is concerned. We could just leave it there and be done, but we want to go to a later point because we want shorter live ranges. We want to sync it along these paths and go to the latest point, after which we'll get in again in trouble because we would get into the path of availability again. So after that particular point, in short, we will not be partially redundant. We'll have some redundancy after this. So those are points are determined using this set of equations and things like we saw. And we also showed that how this PRE covers loop invariant code motion and many interesting other cases to be solved. However, the problem, of course, is that this PRE is not doesn't guarantee complete removal of redundancy, as you see through several examples. And here is where you did this term paper on POPRE and COMPRE, how it allows you to do some changes and get rid of this redundancy by doing some changes to the framework. And I hope that exercise was interesting to learn about these papers, which were really big papers in this area. Shifting gears, then we did SSA, which is a different form. And the main goal of SSA is to be able to bind the static values which are generated at program points to the names uniquely. So what happens is when a name is redefined, there are multiple different kinds of values which statically originate at different program points, but they're all alias with the same name. And because of which we'll kind of lose the correspondence between the value and the name. And our goal is to preserve it, saying that, hey, when we talk about variable B1, it basically means the value which it gets at some program point where B1 is defined. So by doing this clean separation, we are able to very quickly determine many optimizations about the redundancy very fast, and then also many interesting optimizations are fast because we can navigate through these values very, very quickly. So first of all, we saw generation of SSA through phi functions about how to combine the different names at a given program point into a new value and a new name, and minimally. And then we saw some examples of how to generate this SSA, and we also saw how to use it in some ways to do dead code elimination, and some other examples like global value numbering, which is very important, which allows you to determine now A plus B and P plus Q type of equivalences by extending this notion of just lexical identity to the different names. We also saw in this SSA case the sparse conditional constant propagation, how it allows you to detect unreachable paths or blocks, and therefore do more precise constant propagation by using the optimistic lattice. What is an optimistic lattice? An optimistic lattice is when you take a unknown and you marry it with a constant. You do a join of the two. Typically, it would result in an unknown, but here you optimistically assume that unknown to which you are marrying this constant is exactly the same constant, so and you evaluate it to be a constant and propagate. And by doing so, you converge this particular iteration in an optimistic way. And if it indeed rules out any paths on which you have a different constant or a non-constant, then the join is converges to the optimistically to a constant, and that gives you this. So I hope you had a chance to study this through this SCCP and Muchnick handouts and so on, and we covered the other ones here. Finally, changing gears one more time, we went to a different kind of aspect of what we call as program constraints in a non-single assignment setting, which should not be violated in terms of reads and writes and their dependencies, which occurs before what. And we saw that this gives rise to a concept of dependence. And that dependence concept is really important to really find out if reads and writes orders are correctly maintained and in terms of program semantics. And for scalars, we saw this concept, and we also then went into loops and array references, how the writes to the array references and reads, their relative ordering must be preserved, and what it really means to capture that relative ordering in terms of direction vector of the respective iterations. They must execute in a particular order when there is a dependence. For example, the iteration that carries out write must occur before the ones that carry out the read, leading to a flow dependence or generation of a new value within the loop, and is also using that value in the later iteration to carry out some computation. So we have seen three kinds of dependencies. One is the flow, second is anti, which is the reverse of flow. First do a read using old values coming from outside of the loop, and then do a write, generate those values in the loop, but don't use them. And then the output dependence, which is relative order of two different writes and the way they occur from iteration 1 into the iteration 2. The writes orders must also be preserved exactly in the same way. So in short, all the dependencies must be preserved, and if we change the iteration structure of the loop, obviously these dependencies may be satisfied if we don't change the relative order of the respective iterations when the dependency is there. But if we do change the relative order, then we might run into a semantic problem, and that's the thing which we saw. We saw two tests here. One is the Banerjee inequality, and the second is a GCD test, which the Banerjee inequality is in the real domain. The GCD test is in the integer domain. And we also saw this I test, which tells us that even though Banerjee inequality is in the real domain, its results are exact in the integer domain when those conditions get satisfied. And we looked at this particular paper called itest.pdf. Finally, we went through loop restructuring, show you the use of this information, how we can change the relative order, carry out fusion of certain loops which maintain the dependencies, break certain loops into pieces and still be okay. And then we finally saw one of the transformations is loop interchange, wherein the loop's dependence, which was being carried maybe at the outer loop level, now is being carried in a different loop nest level. And as long as the relative order of reads and write iteration points remains the same, this particular dependence is preserved. We saw cases where it is not preserved by loop interchanging, and we also saw how those problems are, wherein the loop carried dependence was in the outer loop is now not preserved by interchanging it. And so there we saw loop skewing, how to push the inner iterations space, skew it with regard to the outer ones, so that the dependence distances between the inner iterations, they follow the similar vector less than as the outer one, and then do the interchange and so on. Last topic, register allocation. Basically, a big principle here is to keep these values which are generated in the program as persistently as possible in the registers. The problems about those are twofold. If the value is aliased and the pointer could go and change the value as per the von Neumann semantics in the memory, then it is not safe, because you would hold the value in a register, you would operate on it, and suddenly there's a pointer dereference which you are ignoring, and that as per the original program, that value would be in the memory and then subsequently used the modified value after this. But by maintaining this in registers and ignoring these pointers, changing that value, what we have done is we have used the stale value, not the one which is generated or modified by the pointer, and that's the violation of safety condition. Same safety condition violation can occur if there is a false dependence between the two references, and or if there is a true dependence and we ignore it, that some other reference to the variable, so the array reference modifies the value, and somehow we ignored it in a similar way, like the pointers. That's a problem. So pointers and arrays are big problems of not keeping in registers, and we had given some exercise of how these things might be tackled in certain cases where there is a guarantee of data flow. So the essential thing there is that data dependence is simply a constraint, but it's not really show anything about data flow. But in certain situations, like for example, A of I plus minus C, we know that there is a data flow between A of I and A of I plus C, given C iterations apart. There is definite guarantee of such data dependence, and we could tackle this data flow, which is guaranteed by allocating registers and by holding these values in registers. But in some other cases, when the data flow guarantee cannot be given, we simply cannot, even though the dependence might exist, there's no guarantee of data flow. And because of that lack of such guarantee, you will be in big trouble trying to do the equation. So now we also saw some techniques of how to determine the liveness of variables from the last use back to the first definition. And this whole range is when we want to ideally maintain this in a register. Of course, in practice, it's not just one single interval, but a combination of different intervals because of the different definitions feeding the same use. That leads to the concept of webs, as we saw earlier, that we must consider the whole web and give it a register. Otherwise, if you give it only on a live range basis, if the control comes from the other side, then there will be a havoc because it will not be the same register. So we got to bind all these to the same registers, and that's why webs. And there we did interference, and we did these Briggs and Chitins things. And some of you have probably seen this in your previous classes. If not, definitely very important part of compilers, register allocation. And at least the theory, you have seen it here. We didn't have time to, of course, implement it because that's typically done in the first class, where you build a register allocation and allocate and bring in the values and do it using code generation, keep it in registers, and see how much benefit they have. Now, before I go into the sort of an optional topic here, I wanted to generally get a feel of are there any questions, and don't be shy because it's good to get things clarified. And we will also have office hours. I'm trying to see when, either most likely on Wednesday, either during the class time, because most likely you won't have any exams then, 5 to 6. That's when I'm thinking. So you can, of course, come back and ask me then. But any topical clarifications or any concept which may be not well understood, it's time to raise that question now. And, we have seen some of the topics a while back. Some of them you did homeworks. Some of them become more clear, I hope. You may have further questions. So let me open the floor and we'll take the questions here. And we can revisit some topic if there is a need to.
There are no suggestions currently on chat.
Okay. Maybe folks want to study a little bit, visit these topics, and come back on. Of course, you can use Piazza, but it is better you come for the live office hours on Wednesday, and we can chat then and see how your questions are better answered, in my opinion, in a live setting, especially since this is supposed to be in-person class. Talking about the final exam now, it will be similar to homeworks and problem solving. Some little, one or two little harder questions, roughly about 6 questions, I would say, maybe one of which could be harder. And some of it could be a little integrative, like register allocation, for example, dependence analysis, that kind of stuff. And be ready to write few algorithms and then solve the rest using known algorithms. And get your concept absolutely crystal clear. If I ask you to explain it, you should be able to confidently get up there and give a beautiful presentation on explanation to the others. That's when you know that you have understood it. So as you study through this, you will come to know maybe, hey, this is not clear to me. This PRE, why is it moving things so early on? And I hope all these kinds of questions that come to your mind, why don't we just keep it to the predecessor basic block, the hoisting of these expressions? These kind of questions, try to answer those using examples, counterexamples, algorithms, and be clear on the data flow equations and why are we hoisting this very busy expression. We cannot, even though it may be determined as very busy, why we cannot hoist it here. And one of the things that I may suggest here is this, that traditional knowledge of data flow, of course, allows us to think in a particular way, but SSA makes it absolutely crystal clear. In other words, we know a particular value, if it's differing in a SSA name, it is definitely a different value. So, for example, in the hoisting case of this very busy expression, if it happens to be the same SSA value, we'll be able to hoist it at an earlier point. However, if there is an join at one of those values, which means that the original value is name is different than the value name at hoisting point, then obviously it is not appropriate to hoist it, because there was another reaching definition in short which you ignored, which was associated with that value. So if it comes from a dominator, SSA wise, you will see that it will bear the same name. So many times it helps, and I will try to make it clear. And in your final exam also, you can answer the question using SSA in your mind, because that is the most clear answer you can give, and you will be able to also give it very quickly. So, of course, the concepts are concepts which SSA is a representation. So make sure you though understand some of them and revisit some of them. In like in PRE, we did not do SSA formulation there, but you may want to quickly think about, hey, how this will look in SSA, just as an example. And we did some examples of CAC being done through SSA and all that. So visualize those. So there will be problem solving questions and some algorithm writing, some original data flow problems, and try to integrate some of these concepts and so on. And if you have any further questions, I'll be happy to see you in Wednesday class or even today.
Professor, yeah, real quick, just as a procedural question, chat was asking if we're going to release like a practice final or like a previous final that was given in the class or something like that.
We usually don't have any such question banks or finals, but I think the best way would be to take now this the papers that you have read, the term papers that you did on PRE, and SSA-wise you understood some techniques better than the traditional data flow, and revisit some of the questions that you did in your homework and see how they look in the new format, or if you were to solve it using SSA, what would you do? Things like that. And but we don't have any practice finals per se because there is a limited set of questions, and we simply don't have such question banks. But if you have any question like that, you can bring it to me, and I'll be happy to. If you're stuck there or if you're having problems, we'll be happy to help you out from the current homeworks or just a question in general that covers that topic. So the best way would be to study would be to watch these videos, get clarity on examples, concepts, come up with your own examples, step through these algorithms. We did some nice exercises like PRE through that code excerpt. You may want to change some of that and see how the PRE was differently and make sure all these concepts are challenged there. So things like that I recommend as DIY sort of exercises. Infeasible paths, we studied that, that adds to imprecision, and we studied some technique. I think we did a very comprehensive job of extending our understanding of data flow analysis and its limitations in terms of pointers, infeasible paths, and so on. So, and then different analyses such as value-based versus lexical-based, things like that. So I would try to be absolutely clear on each one of these different things and morph a little bit of these examples, challenge yourself and try to get answers. And if you have any questions during this exercise, then please make detailed notes of it. Bring it to office hours or post it on Piazza, and we'll be happy to debug your understanding and help you. So that's how I see it. So if there aren't any questions, then what I'm going to do is very quickly, and this is just an overview that I'm going to do of this important topic of register allocation across threads. And just to give a glimpse of how this machine-specific optimization is extremely useful. I picked this paper because it was easy for me. And also it illustrates a brand new topic of register sharing across threads, which has really not been that common. So let me go through that, and we will.
Yeah, just one quick question before we move on, Professor. There was a question asked, which was, would questions based on the material covered in the papers that were assigned for the project or term paper be on the final, or would it be, only on the concepts that we actively covered in class, like lecture?
Good question. So it will not be directly asked the material covered in that paper. However, you should read it for preparing for finals. Because what will happen is, let's say take a topic of PRE. So there might be a twist there in the PRE, the way it was taught in the class. But suddenly, if you had read that particular paper, you might be in a better position to answer some question like that. You see what I mean? So it will not be directly based off the knowledge of that paper. However, for example, something is there is a remnant redundancy remaining. So to answer this kind of question, you'll suddenly be in a better position if you had read that paper, because that was really about the remnant redundancy remaining in how you tackle it, how you remove it. Of course, those are not the questions that only be asked specifically in that paper. Okay, I hope it's clear. Can you guys see my screen for these slides now? Any other questions, by the way?
No questions on chat. It is just a gray screen for me though, so it like what's happened before. I can see your mouse, but not any of the content.
Okay. Let me see. Hopefully now it is better.
Yes, I can see that.
Okay. So this was a work done by my student some time back. And main goal here was how to allocate registers across threads for a network processor, which is kind of unique. So let's talk a little bit about network processors, what they are and where this problem comes into being, and then how do we solve it using compiler techniques. This appeared in PLDI 2004, which is one of our premier conferences. So what are these network processors? So they are all these processors which process these packets at an extremely high rate for throughput purposes, gigabits and all that. And they do lots of processing in flight for these packets, such as QoS, such as the security, the deep inspection, etc., etc. And so these requirements for packet processing, you need a dedicated and a custom processor for this, and which is geared towards throughput. So there is no OS there. There is only firmware which executes on this. And these packets come in and they get processed, very quickly classified, they get processed, and in terms of their IPsec or whatever other stuff they are doing, and then they are sent out. So how does this really work? We typically have several micro engines within this processor, let's say 6 to 10. And there are several threads running on each micro engine in parallel, just like GPUs and all that. And to keep them extremely fast and in terms of execution, because they had to match the line speeds, otherwise the buffering and all will go out of the hand. They share the registers, and these are the different speeds at which they operate, and they share these registers across threads. And let us see how they work in terms of packet processing. And the packets are typically mostly independent, and they exploit parallelism, and they also reduce overheads because again there's no OS. And these registers, and pretty much the packet's important parts are picked up and put it in the registers. They are used there by the threads to look up information, do whatever changes to the packet if needed, and they're all done through registers, and therefore very fast rate the packets are sent out. So again, as I said, they have multiple threads, And of course, sometimes what really happens here is, as you will see, the thread is executing, it needs to go to memory for whatever reasons, because it doesn't find its data in a register. That's a very high latency operation. Because the processor is extremely fast, executing 5 gigahertz and so on. The memory cannot be that fast. The latency is probably 50 to 100 cycles. Now you don't want to idle the micro engine that much, so that leads to a context switch. So the next thread, which is ready in a round robin manner, is scheduled on the micro engine automatically by the hardware. So these kind of things then keep happening, and there are two reasons why they happen. One is the memory, which is like a spill or going to the memory region, and second is context switch, which is explicit context switch, which is carried out by certain instructions. So what we want to do here is we want to reduce spills, because the moment spill is there, you got to go to memory for getting the value of that particular thing which was not there, which is not there in register, and getting that value leads to context switch and slows down that thread and the throughput and so on. So you want to reduce the spills, the same problem but across threads. And different threads could have different requirements, such as one of the threads may be IPsec, the second one may be a QoS. So they could all do different things, and therefore we got to take the set of available registers and divide them up so as to solve this problem of reduction of spills. So let us see how this problem is solved here. So through the example where I'm going to show you. So let's say one thread is executing, and we have certain operations there going on which need a context switch. So let's see how things work here. So the first thread comes and starts executing this instruction which is shown in red. Then the next one, then it goes for reading this particular value which is not there in register, and at that particular point it's going to cost you 50 cycles, let's say. So the micro engine will switch this thread out, and we'll go to the context switch it, and we'll switch to the other thread which is waiting for x is equal to 6. It will start executing that. Then at that particular point, it will read this read y. This particular instruction will get executed. Again, it's a high latency instruction, so it will again context switch back as this thread is suspended to fulfill its request. The request will go out, but it will get fulfilled only after 50 microseconds or 50 cycles. And so in between this, the other thread will get started, and hopefully its data latency is satisfied. The data is already in base, so it will execute that, a plus b, and so on. And then once it again context switch back through a CTX instruction or through another high latency instruction, it will go back and process the next instruction, w is equal to x minus y, and then the execution will progress. So this is how it works. So the context switch here you can see, which leads to a thread switch scheduling rather, is predictable, and it happens on the load instructions when the data is not found in the registers. It also happens on certain instruction which is called as a CTX, and the compiler manages this throughput across all these threads by properly placing these instructions, and then the micro engine uses the context switch so that the micro engine is not idle and gives you the highest throughput. Okay, so that is what is going on. Now, this happens quite frequently, and in terms of this switching, and we got to worry about the throughput because obviously this frequency of switching around is not a good idea. It will degrade the throughput. Although the context switch itself is just one cycle, it's not saving anything else except PC. So it just needs PC to go back to where it left off. It does not save the state because that is going to cost you a lot of cycles. So the implications on the registers side, here we have 4 threads, and they could all share these registers and context switch. But that's the traditional way of doing it. But then what really happens is when the register file is saved, it's completely saved at the point of context switch, because if you're executing a given thread and if you're context switching, the OS will take the complete state, including the registers, will save it, and then it will give it to the second thread and so on. And that context switch is extremely expensive, of several cycles. We don't have that here because obviously it's not going to work. It's a very, very fast processor here. So the other extreme could be that you just take this register file and you just divide it amongst thread. How big is the register file? Typically 128 or 256 registers, let's say for 4 threads. So 32 into 4, something like that. But as I said, here you may have register pressures which may not fit in the 128 or 256. And so what you could do is, instead of doing this, you could allocate uneven number of registers across threads. And however, it is also not safe to share certain registers because, again, as I said, they are not saved across context switch. So if you share some register, let's say some R5 between 2 threads, and R1 put some value there, and so thread 1 put some value there, it is not going to get saved. It is going to get overwritten by the next thread, to which it's context switch. And because of that, the value will be lost, and it will be incorrect to do so. And therefore, you have to do something else. You have to save certain registers, or you have to kind of allocate registers in a certain way that even if you context switch, you won't care whether you lose data there. So how do we do it? So instead of this register file, which is going to be really dedicated because it will not meet the thread's demand for a number of registers, what we'll do is we will try to share some registers across threads and keep some registers as private. So in this particular case, you can see that some registers here will be private to each one of these threads, non-shared. So if we leave values in those, they'll be safe. Upon context switching, no other thread will have an access to them. But then we'll use some shared registers to increase the number of registers visible to each one of these threads so that we can fulfill its register pressure requirements. That's the idea which is followed in this particular paper. How many shared registers, how many private registers, and how to determine which values to keep in private registers at context switch positions, and which values we can leave in the shared registers so that they won't matter. For this particular reason, we use the compiler concepts to determine this particular thing. So the compiler's goal here is to determine shared and private registers to meet the register pressure demands. So what to put in shared register? That's the key issue here. And you can easily see here, live ranges in shared registers must not be used across context switches, because upon the context switch, the values will get lost. So whatever ranges are there between the points of context switch, we know they must be contained, or they must be dead at the point of context switch. And that for those ranges which are not live across the context switch points, we will use the shared registers. Those which are live across will use private registers. That's simple. So we classify the ranges which are live across the context switch positions, and we classify those which are not, and we allocate those separately. And how do we do it? So we build this. This has become the program analysis starts now. So non-switch region of a CFG, we build. What is a non-switch region? So non-switch region is the control flow stays within the given thread without context switching. So we do analysis and determine these large regions, and then determine the interference graph of those values which are intra non-switch region. And then we determine the register pressures, upper and lower bounds there. And then we carry out inter-thread register allocation by giving some registers as private registers to those values which are live across context switch regions, and the ones which are not live, which are completely contained within, we give them as shared to the shared registers. And so this intra-thread and inter-thread, which is, what is intra-thread? Intra-thread is completely private, and inter-thread is shared. So we carry out this division across these, determine some registers for this, some for that. And globally, we take a look at the picture in terms of whether the register pressures are fulfilled, and shift some registers from maybe one thread to the other if needed. Even in this process, we can even restructure the program by putting some context switch instructions in between, and do all other kinds of tricks to maximize the register pressures, to minimize the register pressures, and so on. So a non-switch region is a maximal collected subgraph of CFG without any context C. And next, what we do is find out if live range is fully contained within this. If it is, then what kind of register we can give it to it? We can give it a shared register, because that register will not carry any value which is live across the context. So here is an example, and then we have some kind of a packet processing stuff going on there. So we have the CFG for that, and here is where all the context switch instructions will come because of reads which are inherent there, and the CTX which is inserted by the compiler. So we separate these regions based on these, and you can see that we have, this may be a little faint to see the colors, but you have now separated these into non-switch regions from COM-bench. This is one of the examples. And each connected component of this is an NSR, and this is one NSR, that's another one, that's the third one. Okay, we have these, and you can see that for each one of them, these NSRs, we can give shared registers, because they're all live ranges are internal. Across this context switch, however, we must keep whatever values are live, we must keep them in private registers. So that determines the register requirements of each thread when we analyze it this way. And then we do a give and take, insert maybe some more points in case we need to trade one versus the other, and so on. So after we do this, we do the liveness analysis and find out which are the ranges which are contained within the region and one which are out country, which are live across. So we have 3 of these here. One is for sum, second is for len, third is for something else, and temp also, I believe. And then so we generate this type of live ranges there. And then we have interference graph of different values within and across the NSRs. And here is how it comes out. So these boundary interference graph is basically means that these are the values which are live across, and they are interfering with each other, so they need registers to hold them. And then these are the ones which are intra-region, and basically they could be given some shared registers. So internal interference within each region. So, and then that's how we determine these number of registers which are needed for private purposes and shared purposes. And under this is the overall which we had to satisfy. What is that? So summation of all private registers across all threads plus maximum of the shared registers for each one of the thread, that determines your total amount of registers that you need, and that should be less than equal to the total number of available registers in the micro engine, which is typically 128 or 256 or 512, whatever that is. And so what we want to do here is play with this, how many private PR of I should be there and how many SR of I should be there, so that we keep this equality satisfied, but we reduce the number of spills. So that is the formulation of the problem. So here is some illustration that if we have this green thread which has its private registers, and then black pool is shared across all these. And same is true with the red. Its own private registers are shown in red, and the shared ones are with the black, and so on. If we keep doing that, we must satisfy this inequality. Now the question is, we had to find this range, min PRI, max PRI for each one of the private register ranges and shared register ranges, and for each one of the threads. So how do we do that? So we do this through live range splitting. We can move a particular range from so let's say that we have too much requirement for across, which means that we have too many private registers needed. So we don't have so many. So what do? We of course carry out a split of this live range, which is live across the context switch point, and then do a store at that particular point. So that way we reduce the requirement from a we convert a requirement from a private register to a shared register. Of course, we incur a spill here, but that is inevitable. So that way we keep doing this with minimal introduction of spills. Okay. We try to introduce it minimally so that when we meet this requirement inequality, we are done. So this is a hill climbing kind of an algorithm which will try to reduce the shared register requirement first, and then the private registers requirement and so on, and whatever is the minimum spill cost is the one which it will commit, and this is sort of a heuristic solution. So finally, once we know the number of registers, then we will allocate those for intra-thread allocation using the standard techniques. I will skip this part because again, the details are not really that important. Again, as I said, the live range splitting allows you to convert a range which is live across, which needs a private register, to a shared register. So we did this, and we showed that we are able to do a good balancing of registers across the threads. And we have the numbers in that paper in terms of the performance, throughput, etc., etc. And register sharing, therefore, between threads was controlled by the compiler by using this analysis of no switch regions, and by using the splitting of ranges where the pressure exceeded. And overall, we were able to show that this improves the number of spills. If we just do it based on equal numbers and give it to this, and we don't do this analysis, which is the default case used by the production compiler in use that time from Intel, we showed that we can really outperform it significantly and improve the throughput as well as the register allocation and balance across threads. So this is the paper. Time permitting, I know that probably you won't have time before your finals and all the other stuff is over, but if you feel interested, definitely read it. It was one of the more interesting papers during those times. Even now, there is no sharing of registers per se between threads, except in such extreme cases of performance wherein you want to be able to pass the data and keep the register file flexible in terms of adaptation as per the different pressures, register pressures. So that's the reason for sharing. So it's a very, very unique design. So that's basically it. And that's it for this class as well. I guess I want to thank Nathan for all his help and support. It's a lot of work for this class, for you all. I understand that part. This is a very heavy class, and it's inevitable. We need to go through this to be able to understand LLVM, understand the concepts, papers, be able to marry those together, and also do the theoretical side of it. So I know that it is heavy though, and it does translate to a lot of work for the TA as well as to you. Hopefully this is all worth it, and don't worry about the grades side. Sometimes the grades are a function of what else is going on apart from this class, and I'm sure that you all had some other stuff and which is also taking time or consuming time, blah blah, which might have created somewhat lower scores. But get ready for the finals. I did give the extension for 1 day just with a view to help you out. But if you don't need it, finish it and move on to finals. And good luck for not only this class but for others. And again, as I said, helping you out in the projects, answering your questions, grading, a lot of work for Nathan here. So I do want to thank him for his outstanding job here. And he will finish the grading of the projects and so on, setting up demos with you, because that's not on the critical part of the exam. We will announce the office hours mainly between 5 to 6 on Wednesdays. Those of you who are here already take a note on that. You can come and get your last minute clarification and then be ready for the finals. And one last thing, please do fill out the CIOS. We have a small class here and we want a good response rate. And if you have any suggestions, what to improve, what to stress more, stress less, please put those in. And if you had any ways to thank Nathan or anybody who is associated with the class for their hard work, and there is a way to do it, as you know, through this thank you, professor, and thank you, TA kind of notes. So please do so, but at least fill out the CIOS. And good luck. And then now we'll stop today here and we'll go to the office hours and see you there.